So I'm going to present the slides which I did in AI engineering in San Francisco yesterday. And so I wasn't very sure about presenting this again in any chance, because some of these ideas are very experimental. And also next week I'm going to SAML, so there will probably be tons of new ideas coming up. And I'm not really sure there is another chance to probably present those experiments, which I found some of them are very interesting and inspiring. And I hope you can also get inspired somehow by the ideas in this presentation. So without further ado, let me get started. The question I want to answer today is, so we know these big models get better by thinking longer at inference time. We call that test time compute. Can a small retrieval model do the same thing? Can it get better by just working harder at inference without making the model any bigger? To find out that, I let the agent run Autoresearch overnight, and the answer turned out to be more interesting than simple yes or no. So let me show you what I found. First, let me say what test time compute is. So the idea is very simple. So instead of training a bigger model, you spend more compute at inference time, and you get a better answer back. It shows up in a few familiar forms like best of n sampling, self-consistency, or verifiers that re-ranks the candidates. So Noam Brown from OpenAI put a number on this. He found that a poker bot thinking for 20 seconds gets the same boost as scaling the model for 100,000 times. So that's the promise of test time compute. So the real question for us today is, does this promise also hold for search? So here's a reframe that turns this into a retrieval talk. First of all, search is already test time compute. So think about what you do when you build search. You take a trained embeddings, a trained reranker, a multi-vector retriever, a query expander, and then you wire them together into a pipeline. So you're spending inference to buy relevance. You're not reaching for bigger model. You are basically assembling more search at test time. So the real question isn't whether your model is big enough, it is how much pipeline you assemble at inference and whether that pays off. So there are two ways to build that pipeline, and I will show you both. The first one, version A, is the one that I will go deep on, and here the agent writes a little programs over a frozen encoder. It might chunk the document, z-score, and fuse the different scoring signals and feed the results back. So think of it as a multi-pass algebra on embeddings. The second one, version B, I will come to later. So there we build a small agent that wires up all the retrieval tools like a grab, embed, re-rank over a corpus under a token budget. So it's the same idea, but implemented at two different levels. So let me get started with version A. So version A runs over a small frozen encoder. And there's a common belief that small models cannot improve there, that test time compute exclusively belong to the big reasoning models. But look at where today's embedders come from. So models such as E5 Mistral, Queen3, Embedding Gemma, and even our own Gina embedding V5, they are all distilled from large language model backbones. So that's the dominant recipe today. So if the test time compute lives in the LLM representation space, then this distilled encoder should somehow inherit it, right? Or do they? So that's exactly the question I want to find out. So here's the intuition of how a frozen encoder could improve at test time. So look at the three panels. They go from the simplest way to score a match on the left to the most detailed on the right. On the left, you have a single cosine distance, one vector per document and one vector per query. So that's a frozen cosine baseline. On the right, you have this Colbert-style latent interaction where every query token is matched against every document token. So one can consider it as an extreme case of test time compute. So the interesting part here is the middle panel, the ones that I have outlined in blue. So you can take the same frozen encoder, split the document into sentences, and max over them. So that's what I mean by test time compute. You get closer to latent interaction without new model at all. Just more work on the same embedding model again and again, which you already have. So let me make the question very strict. Right? So how much can a frozen single vector encoder improve at inference alone? And I do mean by restrict, just one frozen encoder behind an API. You can call it as many times as you want, but no retraining, no second model, and no learned parameters. The popular method all break one of these rules, like hide puts an LLM in the query path, GQR as the second retriever, and meta embed trains the new parameters. So we forbid all of three. But even with those constraints, the search space is pretty big. So how do you search it? With Autoresearch, of course. So instead of me handcrafting the programs, agents run the research loop by itself. It changes one line, it runs a short experiment, and if the metric improved, it keeps the change, otherwise it reverts. So it does that over and over all night. And in some sense, it's just a hill climbing, but with an LLM as a mutation function. So Andrew Capacci from Anthropic described it as follows. You are not editing a Python file in the way that research would. You are writing the markdown files that set up autonomous research org. And that loop generates everything that we are about to see. So here's the whole loop in one picture. Just follow the box from the left to right. We have a proposer, which is LLM agent, writes the program over a frozen encoder. The evaluator then scores that program, memory logs the result, and the registry, which the black box on the far right, collects all of them, 144 programs, one per generation. So now see the dashed arrow looping back underneath. That's basically the feedback. Memory conditions the next program, so every round builds on the last one. So let me quickly walk through the 4 pieces. First up is the proposer. It is Opus 4.6 used purely as a mutation function. It reads the current best program and the memory file. And then it edits one Python file and proposes the next one. So there is no human in the inner loop. Now here's the catch. It optimizes exactly the metric you give it, not the metric you mint. So if you reward in-domain performance, and if you reward spending more compute, then that is exactly what it will chase. So whether those improvements hold up anywhere else is a separate question. So the next one is a program. It's just arbitrary Python over the encoder, and the one piece that matters is this embed function. That is a compute budget, and every function calls there re-embed some text, or switches the adapters, or pick a smaller dimensions. One function call here is basically 1 unit of compute. So there are also some other constraints, like the program cannot use any hyperparameters, task routing, or external models. So those constraints force the agent to found a task an agnostic program instead of a config that's secretly tuned for each task. Then comes the evaluator. Every program runs the same 14 discovery tasks, spanning legal, finance, long document, and general retrieval. So we score it via delta NDCG against the cosine baseline, plus a cost ratio, which I will define in a minute. Now here's a design choice that matters the most. So the loop only ever sees these 14 tasks, and there are 19 more that are held out, and the loop never touches them. So later we can ask a very clean question: does what wins here also hold up there? And that gap is a whole experiment. So the last one is the memory. It is basically a simple JSON-L file with 1 row per program, and each row stores the scores, the cost, the parent, and a short lesson. The proposer reads this file before every round so that the whole search compounds over time. But compounding cuts both ways, right? It builds on real ones, yes, but it also compounds whatever bias the objective has. A biased metric doesn't just mislead one program, it steers the entire family tree. So now let me set up the models that we use here. We run the search on a single encoder, which is our Gina embedding v5 Nano, only 200 parameters, and SOTA on multilingual retrieval. We also choose Nano because as our discovery phase model because it is very small, therefore reduce the cycle time of each experiment. We hold out bigger model from the same family plus two unseen families like Gemma and Kun, which sharing no training data, no tokenizer, no backbones with the discovery mode. And we also hold out 19 evaluation tasks, the ones the loop never sees. So one program that we get discovered by using Gina v5 Nano, it has to generalize to all encoders and all tasks. So now before any results, let me introduce the cost of test time compute. So it comes down to just one number, C. And that's just the number of extra forward passes through the encoder. So let me explain it with two cards on the slides. So they basically do the same thing. They mix in some neighborhood information and then rescore that. The card on the left is called self-centroid. It averages the document vectors that you already computed, and there is no new forward pass. That means its cost C equals 1. The card on the right is called first sentence. It re-embeds the first sentence of the top document, which is a brand new forward pass. So there the C is greater than 1. One reuse the geometry that you already have, the other spend compute on new text. So now we can price the compute. We run that exact same loop under two different rubrics. The first one is compute rubric. It admits a program only if its in-domain performance beats every program before it. So it actually pushes to spend more compute at inference time. The second one is called transfer rubric. It keeps a program only if it improves on the validation split, with nothing getting worse. And it gets no reward at all for spending compute. And to be clear, that validation split still comes from what the loop can see. Neither rubric ever touch the 19 final held out tasks or the unseen encoders. So that is basically the two rubric running under the same loop. So let's start with the compute rubric. When you tell it to spend more compute, it draws this very beautiful clean curve. The x-axis is the compute you spend on the log scale, and the y-axis is the score. So there are 144 programs, and 12 of them sit on the parent front. The cost running from just over 1 all the way up to almost 15 times. And the in-domain score climbs nicely. It more than triples across that front. This looks exactly like the test time compute scaling, more compute, more quality. So if I stop here, you will be sold. But this is all still in-domain performance, so we haven't run the held-out test yet. So let's take a quick look on these 12 programs and then run them on held-out data. So here are those 12 programs drawn as little diagrams. You don't have to read into each one. The only thing I want you to take away from this is that they are all training-free recombinations of the same frozen encoder. Just chunking, scoring, feedback, and fusion. The cost climbs steadily from left to right, so it does look like a clean scaling story, but the improvement, as you will see, do not. So now we run the 12 programs on the held-out data, and the same chart as before, compute runs left to the right, scores runs up and down. The dashed line across the middle is a baseline. So look at the pink line, that is a compute rubric, and it's basically flat, hugging 0 all the way out. So out of domain, more compute buys you essentially nothing. Now let's look at the blue dots, which is the transfer program. They all sit on the left because they are very cheap. And everyone is above the pink line. So the cheapest one at zero extra cost. So it will still be most expensive program. So that means more compute did not transfer, but the chip structure did. So if we plot every program against every held out task, we get this heat map. So there are 4 blocks, basically corresponds to the 4 encoders. 3 of them were never seen in the discovery phase, and in each block, the rows are the programs. The columns are the 19 tasks, and green means improvement, red or pink means the drop. The picture is genuinely mixed. Compute helps in about half of the cells, but the improvements are uneven. A few of them even drop sharply. So on average, it comes out flat. Compute does help in places, but it doesn't help reliably on new encoders. So now let's look at the other rubric, the transfer rubric. It picks 6 completely different programs. On this 12 compute ones, they are all very cheap, almost 1.5 times compute cost. The best one wins 83% on the held out data, and it never loses on single task. So now what do these programs actually do? They are basically just touching the query and document vectors that you already have, then add a small cheap mask on top of that. So some nudge the query towards the document it already likes, some pick a new few directions in the space and rescore the vectors along those directions. So that small bit of restructuring is enough to pull the right document up. And that's all recombination, no new model. And this transfer actually generalize across models and languages. So remember, we just used GNF v5 Nano for the discovery, and this improvement actually generalized to all 4 encoders. And the biggest bar are Gemma and Quinn. Those are the 2 families it never saw in the discovery phase. So it isn't some quirk of one model, it rides on general embedding geometry. So that is basically the version A. Right? We have a frozen encoder where chip structure won and raw compute didn't. And Autoresearch is how we found that. But let me move one level up. And from the model layer, now we move to the search pipeline. And you will see that the same test time compute idea reflected as well as the pipeline level. So in 2025, we had this deep research or agentic search product, which basically is a loop on the open web. In 2026, we have a long horizon task, which adds implementation, sandbox, evals on top of the retrieval, running for hours. So both patterns need more looping and more compute at test time. So to study those agentic search at test time, I built 3 small open source projects. So if you have been following me on LinkedIn or like X, so you probably already saw these projects. The first one is data room. You give it a token budget, it searches, it reads, it writes over and over until it packs everything into a zip file. I call it a data room because it kind of reminds me the data rooms I prepared for the investors back when I was a founder. That zip is a distilled corpus of the open web ready for the next agent or LLM to consume. And notice the token economy here. So you are basically exploring the web and build the corpus with a very cheap tokens from small language models such as Quinn 27B or 35B A3B. And then you save the expensive frontier tokens for later, for exploitation. The second one is the search box. So this is the test bed to study agentic search and tool calling. And it is designed to be air-gapped. So the agent has no internet access. So you lock an agent inside the box, you give it a data room, you ask questions, and the agent, in order to answer this question, it has to assemble a search pipeline at test time. So a pipeline that made of local tools, so things like a grab, embed, rerank. And that let you ask some very interesting research questions, such as which tool does the agent reach for first? And is grab all you need, or does forcing more compute help on the hard question? And well, the agent build a pipeline that it can reuse later. So search box is just a test bed to study those questions. So how do you evaluate the agentic search like that? Well, you need hard questions. And that's the third project, which is knowledge graph. It turns the corpus into a knowledge graph where each fact is becoming an edge and linking from the subject to an object. Then we walk the longest path through that graph. The longest chain therefore becomes a multi-hop questions that no single passage can answer. The agent has to spend real test time compute connecting facts together. So it's a tool for building private verifier. So let's connect all the dots together. So both version A and version B are doing the same thing. They both spend compute at test time. And neither one grows the model. In version A, we found a special embedding algebra over a frozen encoder that improves the search relevance. In version B, we build a stack to find the best pipeline. We use the data room to maximize recall, and we use search box to maximize precision. And we use the knowledge graph to build evaluation from those hard questions. So this finally gives us a pipeline with strong search relevance. So it is like two levels, but they share the same bed, which is spending more test time compute, not on bigger model. So finally, let me leave with this one big picture is that I keep saying search is test time compute. So don't reach for bigger model, do more search at inference time instead. And you also don't have to design all the search by hand. Autoresearch discovers it for you, probably just overnight. And that's how we scale test time compute.